Okay. So last time we did these things called, he's German, so the man's name is Euler. They're called Euler Approximations. If you call them Euler Approximations, I'll know what you mean. So that was, as we saw, a numerical way to think about, to answer the question, if you have the derivative, how can you say something about values for the function? So previously, let's see. So the first thing we did was we talked about just antiderivatives. If you have f prime, then you can say what f is, as long as f prime is an answer to a question you already know. So for example, if f prime is e to the x, then you know f is e to the x just from experience. Okay, so those are simple antiderivatives. Then we talked about doing this thing numerically, which we called Euler Approximations. And the idea was that you could use the idea for the linear approximation with a tangent line, but you could break it down into more than just one calculation with one tangent line. You could say, let's use more than one straight line approximations. And as far as the formula goes, it looked like, the formula in the calculation looks like this. And that was the last thing we did. And we also drew the graph for that. The idea being that at each, instead of just drawing one straight line, every term that you're adding on represents the endpoint, if you will. So every term represents a new amount that you've added and arriving at a new point. So then adding this point, adding this amount represents getting to there, and then adding this amount represents getting to there. Okay. So does that make sense? Instead of just going along one tangent line, you've got all these little straight lines. Okay. So in this case, there's 3 steps. So we've got it broken down into 3 straight lines. Okay. So what I want to do right now is I want to talk about what does this look like. I want to take this graphical picture and extend it to talk about what does the graph look like in general when you talk about solving these kinds of questions. Okay. So the graph. So saying something like you know f prime and you want to find f, that's called a differential equation. So differential coming, if you like, coming from find the derivative or differentiate. Okay. So you can take the actual differential equation and represent that entire thing graphically. Not just your little Euler approximation with a couple straight line segments, but you can represent the entire thing graphically. So how do you do that? Well, once again, we're going to go back to the simple equation that we started with, which was the derivative equals 2x. So here I'm using dy dx notation just to remind you that it's a relationship between x and y, or to think about that. Okay. So what is the differential equation derivative equals 2x? What does that mean? What that means is no matter where you are, the derivative, which is the slope, is 2x. So how can you represent that graphically? That's what we're going to look at right now. Okay. So when you say it's a parabola, you're already describing the function itself. And I'm saying, whoa, slow your horses. You've gone too far. I just want to talk about what does it mean to say the slope is 2x? And how can you represent the statement the slope is 2x graphically without solving anything? Okay. So what do you mean by a line?
Up 2 over right 1.
This is a line with a slope
Okay.
of 2.
So if you draw, let's say this, what's the slope? Approximately. The slope on that line is, let's say, 2. Okay. But let's see. Oh, okay. So let's go to my second thing. So let's say on this graph in this plane, we're at the point 4, 7. At the point 4 comma 7, what should the slope be?
Same thing.
Well, what does the formula tell us the slope is? The formula says the slope is 2x. So at the point 4 comma 7, what is the slope? It's 2x. So at the point 4 comma 7, what is that?
With the slope, you mean when you ask what the slope is, you're asking what the slope of the original function.
Exactly. Everything's oriented relative to the original function. Yeah, the slope is 8. The slope is going to be 2x, which is 2 times 4, so the slope is 8. So now what about, let's go back to the first one, what about at the point 1 comma 1, what's the slope? Should be 2. What about the point negative 2 comma 3, what's the slope? All right. And at 5 comma 2, the slope is 10. So this tells us that the slope is always changing. Well, that's right. That's what we expect because we're not in algebra anymore. We're talking about situations where not linear functions, the slope is always changing. Now the question is, how do we represent this information? Okay, so here's what we can do. So here's the point 1 comma 1 right over here. And I want to represent the fact that the slope is 2. And the way I'm going to do that graphically is with a short tangent line. So that lets me know that when the graph goes through that point, that should be the tangent line. Okay, so what about the point 4 comma 7? 4 comma 7 is right around here. And the slope should be 8. That's pretty steep. So something like that. Okay. Now what about at the point negative 2 comma 3? Negative 2 comma 3 is right around here. The slope should be negative 4. So like that. And 5 comma negative 2, slope was 10, so really steep. It's hard to draw really steep lines. They're basically just almost vertical. Okay. Now, of course, these are sort of like little pieces in a jigsaw puzzle. Yeah.
If I were to guess, there's an asymptote here. Because we have two really steep next to each other, so I'm assuming there's an asymptote right between them.
Well, what does an asymptote mean in terms of the slope?
The slope.
Yeah. So hypothetically, if there was an asymptote, what would the slope of the line be, of the graph be as it gets close to that asymptote?
Infinity or the graph doesn't reach the solid.
Right. So what would the slope be approaching as it approaches the asymptote? Right. The slope is approaching infinity. Okay. Do we ever have a slope of infinity? No, because the slope is 2x. So there's no asymptote. At least not in that sense. Okay. So at this point, we've only filled in 4 points, but we can fill in some more. Okay, so I'm just going to do that really quickly. Oh, by the way, let's fill in a nice one here. What about the point 0 comma 3? What's the slope?
0.
Yeah, 2 times 0 equals 0. Okay, so when x is 0, the slope is 0. So you got those tangent lines. And then you've got, let's see, then you've got when x is 1, the slope is 2. We know when x is 2, the slope is 4. And have things like this. Okay. And I should never neglect the the bottom half of the graph, so we got little pieces like that. Okay. And of course also on the left side of the graph, well, we know the x values are going to be negative, so 2x also going to be negative, so we have lots of things like that. And again, I'm starting with a relatively easy one just so we can say nice things about it. And then it gets even steeper out here, to the extent that I can draw nice steep lines. Let's see. Something like that. Okay. Okay. So that's So that is a bunch of short tangent lines, each one telling us what the slope is at that point. So that's called the slope field. Okay. Now, what's the function? Right, so we already talked about this in the symbolic sense, it's x squared plus c. Now remember that the idea is that we don't know what the actual original function is unless we have some information that lets us solve the initial condition. So let's assume, again, the same initial condition. Suppose we know that f of 1 equals 2. Forget about the symbols, just look at the graph and the slope field. What does that tell us about what the solution should be? Well, it tells us that the solution should include which point?
x1, y2.
X equals 1, y equals 2. So it should include the point 1, comma 2. Okay. As soon as we know that it goes through that point, now we can just pretend that we're a river and we have to go with the flow. Go with the flow means follow your tangent lines. So I'm just going to draw whatever the field tells me to draw. So first I'm going to go forward, then I'll go backwards. So going forward, I have to follow these tangent lines. Okay. And then also this way I have to follow the tangent lines. All right, I didn't quite get the end part right. Should be a little, there you go. Okay. So aside from my awesome drawing ability, what does this graph kind of look like? Kind of looks like a parabola. And we know just from doing it symbolically, that's what it's supposed to be. But this is a way that you can solve it visually. Yeah.
Did you ever try to with a computer to fill up the whole field? Because then I feel like I visualize the way it will look. Yeah, like a real river.
Like that.
The idea that it's like 1 point ahead, is it like x squared plus 1?
Yeah, okay. So, all right. So the x squared plus 1 part, I didn't totally nail that. Because if I had nailed that, it really should have gone through that point right there. So my drawing was a little bad. But yeah, if I was really good at drawing this, that's what would have happened. It would have gone through that point. Which we know from the symbolic answer, that's what should be happening. Yeah. Okay. But let's leave it to the computer. I think the computer did it better. Yeah.
Like, what's the purpose of having, like, at each point, if you can already predict, like, you know, they would line up to a specific, like, instead of just choosing random points, can we just base the points on the slope? Because you pick negative stuff, but you didn't even draw a line over it. Instead of just making, you know, the whole thing with tangent lines.
Right.
Just stick with the parabola we already know.
Right. Okay. So let me answer that question in like a couple different ways. First of all, I'm starting with a really, really easy example, so we kind of already know the answer. What if you didn't already know the answer? So for example, what if I said, dy dx equals e to the x squared. Actually, let's make it e to the negative x squared. What's the original function? Something plus c, right?
That's it would be hard. It's like
Yeah.
3 layers.
Not only is it hard, it's actually, in a sense, impossible. There's no closed function for what the original. There's no closed expression for what the original function is. The only way to do this is to do numerically with Euler approximations, or to draw a graph getting some kind of nice approximation. It's the only way to do it. So you could graph this. I'm not going to, I know approximately what it looks like. So you would wind up with, let's see. Oh, this is this one. This is the, right, okay. So you would get things like this, and then this, and then these would be like this, and then this. Well, those shouldn't be exactly flat. They should be almost flat. So anyway, long story short, you wind up with something, you would wind up with a slope field something like this. Kind of faking it by hand here, but that's the idea. Okay. So then when you drew this in, you would get something that looks like this. Now, of course, there was no way for you to know that ahead of time just from looking at the original equation. So one of the things that the graph can do is it can let you understand sort of what's happening in terms of up and down instantly just by looking at the slope field. Obviously, now when I was in school, I had to draw these by hand. So drawing this by hand, if you don't know ahead of time where you're supposed to draw, it takes a long time to figure everything out. But you guys are actually going to have a chance to use the software that generated this picture. Question? Oh, you don't. You don't unless I tell you. So for example, it could have been maybe you were supposed to start over here. Right. Yeah, you don't know. I was drawing one possible solution. But right, so as we know from our work last time, talking about antiderivatives, there's going to be basically infinitely many solutions depending upon what your constant is. Okay. So yes, you could have this one, you could have this one, that's a solution, blah, blah, blah. Okay. Well, my drawing is terrible, but that's the idea. Okay. So the point is, so not only can we use this technique to talk about differential equations where we already know the answer as far as symbolically, but we can use it to talk about things where we have no idea what the answer is. So here's one example of a differential equation where we don't really know what the original function is. All right. And in fact, we can use it to look at some absolutely outlandish things. For example, dy dx equals y. So I've written down the derivative in terms of y. That seems to break all kinds of rules for us. Right? That's not how we write stuff down. It should be f prime of x. It should be an expression in x. But once you understand the idea of a differential equation, you realize it doesn't have to be. So for example, at the point 1, 3, what's the slope? The slope is 3. And at the point 2, 1, what's the slope? The slope is 1. So I can make the most absolutely outlandish and outrageous differential equation expression for dy dx, and you can still draw the slope field. And once you draw the slope field, you can do things like, oh, I can look at this and I can kind of know where the graph is going because you just follow the slope lines. Even though we don't necessarily know what the original function is. So particularly for cases like that, drawing slope fields is a nice way to get an overall view of what the behavior of the original function is, even without knowing the original function. And we're going to say some more things about this because, as I'll talk about either later or next time, it turns out that differential equations come up everywhere. Everywhere. In all the sciences. So scientists are doing stuff like this all the time. Okay. Okay. And here I put another very unusual differential equation. Dy dx equals negative 0.5 times y minus 2. Doesn't seem like an expression we should be thinking about. However, two things. First of all, it turns out that this differential equations in this form are actually a very special kind of a differential equation. They're called Newton's law of cooling. And this describes the temperature of an object sitting in, for example, a room or an ambient temperature that's different from its own temperature. So this shows you what happens to the temperature of that object over time as it cools. So that is one example. And we'll talk more about applications of this stuff later on. I just wanted to throw one fancy little example at you. Okay. Okay. So we'll come back to that. All right. So any questions? Any questions about the basic idea of slope fields? Everybody understand what a slope field is? No? Okay. So what is confusing you?
Basically, this part about tangent lines, being like almost everywhere, and then you have to go on the slope. Read that the parabola.
Okay. So think back. So in order to connect it, to help you understand it, I'm going to connect it to other stuff that we've done. So if you know, okay. So if we know, where is this? Okay. So if we know the derivative is 2x, what's the original function?
X squared
Plus c. Exactly. Okay. So the thing is, it could be x squared plus 1, x squared plus 2, x squared minus 7, da-da-da-da. So basically what you have is a bunch of different parabolas, which we'll call a family. So you can have a family of different parabolas, all of which could be the solution, assuming you don't know anything else. So how can you represent that graphically? Well, graphically, the solutions could be this, and that's the terrible drawing. Okay. Could be that, it could be that one, it could be that one, it could be that one. So what I'm doing here is I'm drawing all the different possible solutions. So where plus c, a different plus c is represented by each each function that I've drawn. So far so good? Okay. So what does that have to do with the slope field? Well, every possible solution that I've drawn, what I've done is, and what I actually did at the very beginning, was I said, well, the slope at every single point on the function is 2x. So for example, what does that mean? Let's just look at this one. So right over here, at this point on that possible solution, the x value is 1, so the slope must be 2. So you could draw a little tangent line to represent the fact, you could draw a little tangent line, and that little tangent line would have a slope of 2. Okay. Now, of course, you could draw a long tangent line, but then that would just cross over other graphs and make things confusing. So that's why I always refer to drawing a short tangent line. Okay. Similarly, let's look at the other possible solutions. Well, the other possible solution, right over here. When x equals 1, what's the slope? 2. Right. So for every single solution, well, and this isn't always true, but it's true for this differential equation. Since the slope is always 2x, then on any solution graph that I draw, when x is 1, the slope will be 2. So how can I represent that fact? Well, here, not very good, but there you go. I'm drawing a little tangent line that has a slope of 2. On this other graph, I can draw a little tangent line. That slope is 2. On this graph, I can draw a little tangent line. That's not a tangent line, but you get the idea. Okay. That slope is 2. On this graph, I'm drawing a tangent line, and that slope is 2, et cetera, et cetera, et cetera. So every single graph, when it hits the point where x equals 1, it's going to have a slope of 2. And I can represent that graphically by drawing this short tangent line to show me what the tangent line will be at that point. So and of course I can talk about when x equals 2 or x equals -3, blah, 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 and everything will have its own tangent line. The thing that's a mess is that there's this plus c business, in that it could be any one of these graphs. So basically what I'm doing is I'm filling in every tangent line at every point on every possible solution, because I don't know which solution it is. And only when I get this thing called the initial condition that tells me which point it goes through, only when I'm told that do I actually know which curve to draw. But until then, I have, if you like, all these solution curves. Each of them has all these different tangent lines along it. Okay. So because we're given f prime, we don't draw the solution curve. We don't draw the original function and then the tangent lines. First, we draw the tangent lines, because we're starting with the formula that tells us the slope. So you can draw in the tangent lines. And then once you have the tangent lines, you can say, oh, those kind of tell me which direction to head in, so then I kind of know how to draw the original function. So this is why, and so now you get the picture of why integration is the opposite of differentiation. With differentiation, you say, here's the original function, what's the derivative? Or graphically, that means what's the slope? But we're going backwards. We're saying, if you tell me the slope, or in this case, all the slopes, then I can tell you what the original function is. So it's backwards of how you spend all of Calc 1 thinking. And that's the idea.